Hi, my name is Leafia Sheraden Cox. This summer I had the amazing opportunity to work with Alex Parker and Alejandro Soto at Southwest Research Institute on designing and testing a low-cost fluorimeter for use in for mineral analysis in the field. So first things first, what's a fluorimeter? In its simplest terms, a fluorimeter is an instrument that just detects and measures fluorescence, so light emitted from a rock. Its general setup requires a light source, an excitation filter, then a sample, which then fluoresces, and then an emission filter and a detector. It's a very, very simple setup. So next, why build one? Well, there is this method of spectroscopy called laser-activated spectroscopy, and it's really, really common for in-field sample analysis, particularly in space missions, because you can do it from a distance instead of having to be right up against it. However, the most common methods, which are Raman and LIBS, are expensive and complex. So over on the right of the slide is an image of the Curiosity rover, which has a built-in LIBS instrument that does mineral analysis from a distance. And then over on the left above is an image of the Mars 2020 rover payload. So there's two spectroscopic instruments on that rover. There's a Raman and a LIBS. And then, so up at the top in the center is a Raman spectrometer. The cheapest ones that I could find on the market is around $12,000. Below that is a LIBS instrument. That LIBS instrument is around $30,500, and that's the cheapest one that I could find on the internet. So as you can see, they're very, very expensive. So why build a fluorimeter? Well, because it's simple and it's cheap, and it can do bulk mineral analysis in a very effective manner for selecting sample sites in things like crewed missions. It's not as detailed as the Raman or the LIBS, but it can give you enough information so you can say, all right, this is a point of interest, we'll come back with the more advanced instruments. And it's effective because fluorescence is a property that is inherent in certain chemicals and compounds. And 15% of all rocks fluoresce to the human eye, but that's only in the visible wavelength. A lot more fluoresce in the UV and other wavelengths. So if you have the right excitation, then you can detect that fluorescence, which is why with a more sensitive instrument, something that's more sensitive than the human eye, you can get a lot more information out of such a simple device. And above in the figures, we have just an example of fluorescence itself. There's the willemite and calcite on the left of the screen that is under normal white light, and then on the right, it's under a UV light source, and you can see that it changes color and it's a different color. So here are the requirements for the instrument. It has to be low cost, has to be easy to build, made from commercially available materials, easily calibrated, compact, easy to operate, open source, fast, and field portable. All of these are because our primary goal is that we can make this instrument so that it can be easily replicated. It can be used by anybody, anywhere, so it could have outreach opportunities, amateur geologist who wants to go and analyze their local minerals can go build it, calibrate it, and use it. And so it's really important that it's adjustable. It doesn't have barriers like proprietary software. It has to be able to be troubleshooted on the go. It has to be small and light and much less than $12,000 or $30,500. And it has to be fast because you can't sit there with a sample and stand there for 3 minutes while it takes one measurement. So now the instrument, the primary components are listed. The first thing is this Blackboard C. This is an Arduino. It's a microcontroller. It's really cheap, and it's the what's doing all the hard stuff of telling the instrument to take the data and then retrieving it. Then there's the triad spectroscopy sensor, this instrument. This has all the sensors on it, built in. It's nice, compact from SparkFun. Then there's the Raspberry Pi, which is the control computer. It runs Python and does all the data analysis. There's the touchscreen LCD, which is just for in-field adjustments. This is the LCD, and the Raspberry Pi is underneath. Then there is 2 UV light sources. There's a UVA LED and a UVC LED for 2 different ranges of wavelengths in the UV. Then there is a UV filter inserted into the instrument to reduce the light leakage that comes from the reflectance. And then finally, just to correlate position and time to the samples that you measure, there is an USB GPS dongle. In total, it comes to around $300. So it's way cheaper than that $12,000 Raman instrument. Now, here's a labeled diagram of the instrument. I also have it here with me. As you can see, it's very compact. It's just a push-button operation, and everything is centered into this primary area, which is where the Arduino lives, and then the UV fluorescent, the UV light sources are in this little cap here, separated from the sample by the filter. And you just stick the sample right in the hole, you shroud it, and wrap it up like a little burrito. And then you press the button, the computer goes, and then it gives you your information. It's very fast, very quick. It's 3 seconds for each measurement. So in all, we achieved the primary goals. So in order to make this instrument useful, we had to build a library of characteristic spectrum. We contacted the Denver Museum of Natural Science with a list of relevant minerals to our case study, which I will get to later. And they provided us with a range of 72 samples with at least 2 representatives from each mineral class. And we measured them, averaged all the spectra by mineral class, and built it as a reference library. As you can see, we have things like albite, andesite, amphibole. We have some hornblende in there. We have some very blatantly fluorescent minerals such as willemite and calcite. So we tried to cover all our bases in terms of the end members of the case study. So in order to make the reference library useful, we had to have some sort of model that correlated it to the measurements that we took in the field. So we built a chi-squared minimization model, which is basically with the data that you have, plot it, and then plot all the reference things that you need, and how far away is the measurement from those characteristic spectra. If they're closer, it's more likely to be that mineral. So it's just like basically a distance measurement. So as you can see, in this plot, we have albite, augite, magnetite, and olivine from the database. And then we averaged a selection of 10 samples from sites AP85 all the way to 95. And then the model is in the dotted line, the dotted blue line. And you can see it's plotted in UVC, reflectance, and UVA along the wavelengths, which there are 18 different wavelengths that it's plotting against. And based on the chi-square minimization model, we have a prediction of around 50% augite, and then 25% magnetite, 16% olivine, and 4.8% albite, which is plagioclase. So this is actually relatively reasonable results given the composition of the case study, which was in the Palisade database. The Palisade database is in Fort Lee, New Jersey. It's extremely well studied, and it's also a lunar analog site due to its composition and formation. We took measurements of samples in the field along several transects, and they were analyzed for the bulk composition based on those selected 4 end members: albite, augite, magnetite, and olivine. And then the measurements spanned a total horizontal distance of around 2,200 feet, and each sample was taken around 25 feet apart. So once we had our measurements, we analyzed the performance. The measurements were averaged and plotted in comparison to the characteristic spectra, just like in the figure earlier. This is for sample OLB1, and you can see it plotted in black and the model plotted in the dotted blue, and it gives a prediction of around 90% composition, which is very reasonable given the location and the high pyroxene content of this region of the sill. Now, there were, of course, some problems. The UVC, particularly, there wasn't enough current going to it because there are limits on the current for the microcontroller to provide. So it suffered a lot of issues due to the fact that it was there was such little illumination and such little light coming through that it was basically saying 0 or 1 all the time. And so you can see that it's like a really bumpy spectra. That bright pink line, that's the unaverage. But when we took 150 measurements of the same sample in a hand sample and averaged them all together, we got a much more reasonable and much more smooth UVC spectrum that's in black, which is a little bit hidden, but it actually follows the model a lot closer. So that was one way to get around the discretization noise. So overall performance, there is a paper going in NASLN in 1995, which was done, they analyzed the composition of the sill volumetrically and by eye, and they came up with these trends of pyroxene and plagioclase by volume. When we plotted our measurements, we did it by area. We calculated by area rather than volumetric, so the percentages don't really match up. But you can see that the trends of the pyroxene coverage does actually replicate the shape of the pyroxene coverage that they found by eye volumetrically. The plagioclase doesn't really, but there are some explanations as to why that might be the case. One being volumetric, two being the fact that they were doing it by eye, we were using a measurement system, and also our mineral database might be in some way introducing a lot of error. Now, in terms of future work, I have the privilege of continuing to work on this during the school year. So we need to deal with the UVA light leakage. As you could see from the spectra earlier, it was very spiky. That's primarily due to the light leakage that's getting through the filter. We need more current for the UVC so that we don't necessarily have to take 150 measurements of each sample. We need more measurements in general just to keep testing it. We need to be able to replicate it. We need to be able to make this using completely different components that were purchased in the same place so that we can make sure that it's not just this computer works really, really well and this one doesn't. So I will take it to school and build another one. We also want to expand the library, potentially to include some meteorite samples so that we can apply it to the moon and other small bodies, because that is one of the primary goals. And then in terms of applications, it has a lot more applications outside of just what we are looking at. There are, you can use fluorescence for identifying water quality, plant health, contamination, and a recent paper just published an instrument that they used fluorescence to study breast cancer. So there's a lot of different applications. I'd like to thank the Denver Museum of Nature and Science for their access to the mineral collection. I'd like to thank UNAVCO staff for all their assistance and guidance. And a special thank you to my communication mentor, Jen Reeves, Lon Abbott, Rachel Havernack, Emily Fairfax, Becky Simon for their mentorship, and also my project mentors, Alex Parker and Alejandro Soto, and the participants of the field campaign. And also, thank you to the NSF for funding me. Thank you for listening. Any questions?
Back in the corner, hang on. Wait, where is there one closer? I'll come back, Alex.
Okay, so when you put up the percent composition of the different samples, I was just wondering how accurate that prediction is, like within a percentage or even less than that.
So we tried to, by going into the field, we tried to have the more advanced laser spectroscopy methods cross-check us. We had a LIBS and a Raman both in the field to try and determine what the composition was that way. However, neither of those instruments actually picked up on anything. So ours is the most effective in terms of getting actual data that could be actually human readable and not just a string of numbers that the computer couldn't understand. So we don't quite know, but we were determining the performance based on comparisons to Goring and Naslin's results, because they have those pyroxene and plagioclase and augite and albite percentages based on height in the sill. And so we were going with, okay, we're this high in the sill, and this is the percent composition that we're getting, and this is what they got. So it's approximately, it's working. It's giving reasonable results. So.
Okay, thank you.
So you said you wanted to expand your library by analyzing more minerals for like moon and everything. So what additions would you have to make to your device to be able to make it space rated? So
space rated instruments, they're not made from consumer off-the-shelf products, obviously. They cost around $1 million for a really, really cheap one. But since this one is so simple and very fast and easy to build, it would be in that very low range of space-rated instruments. And by adding minerals that are found on small objects in the solar system, such as the asteroid belt and things like that, you could, in theory, make a bunch of these, send them out in a flyby mission, have the vehicle just drop like 100 of these on the surface. They would sit there, take measurements, die, and then you'd have your data. And so it'd be, that's one of the conceptual applications for space missions for this instrument. Did that answer your question? Okay.
Great. I think we're out of time for questions, but Leafia will be around during lunch, I'm sure, and happy to answer questions.
I also have the instrument, so if you want a closer up demo, I have that.
Yes. She has lots of. All right, let's give Leafia another round of applause.